Dear students, in the last class, I told you about the pin diagram of 8086. In that pin diagram, the 32nd pin, which describes about the whether this 8086 microprocessor is going to operate in a single processor mode or a multiprocessor mode. So the 32nd pin, you can see here that minimum or maximum mode. Here the minimum is connected with the VCC is connected with the pin here. So it indirectly tells you about the processor is going to act as a minimum mode, that is single processor mode. If it is going to act as a minimum mode, you can able to see how the microprocessor is going to operate. So in a minimum mode, does not care about any other peripherals or any other processors is going to connect. So it cares only about what all the peripherals internally connected with him, like a memory or maybe some data buffers. First, you can see here the clock generator 8284, which gives the clock pulses to the 8086 microprocessor with the help of a crystal oscillator. You know it. Okay, the operating frequency is nothing but 5 megahertz. So through this ready and reset pins, we can able to wake up the 8086 microprocessors. And here also you can able to see that some latches are available and trans receivers are available. Trans receivers you can combinedly call it as transceivers. So here we are going to share the address and data bus in the common. So the every first T1 state, the bus is going to act as a address bus. So through this, you can see that AD0 to AD15, the pins are shared. So either it can act as an address and also as a data. So through this bus, you can see that whenever the first T state, the latches, you can see there are 2 or 3 latches because every one is of 8 bit. Every latch is of 8 bit. So 8 plus behind that one, another one is 16 and another one which may be fully occupied or maybe partially occupied. So 8 plus 8, 16 plus maybe 4. So that A0 to A19 can be connected through the latches. The latch can be able to hold the address for a few time because the bus has to gone through the memory. So through this time, the latches can be holded. After that, the address bus can be act as a data bus whenever it go to the memory. The memory may be of RAM or maybe ROM. Either if you consider any peripherals like a pen drive or a CD drive or whatever maybe thing that can be considered as I/O, input or output device. So here, which chip is going to select? You can see that CS, there's nothing but chip select, which is active low signal. Which chip you're going to select through the CS logic? You can see that through the CS logic, you can able to select whether even address chip select in RAM or odd address select in RAM. Also, like for ROM, even address chip select or ROM address select. So for every memory, we are having odd address as well as even address because it is a 16-bit microprocessor. They will take 2 consecutive memory locations for every data we are going to store. So through this trans receiver, through this bus, the data will be considered here from D0 to D15. That is, we are separating the A0 and the D0 through the help of a ALE pin. It's like a strobe. So, okay, after the T1 state, the T2 states, the data will be activated to the trans receivers. We are going to receive the data, are going to store the data. Here you can see able to see the trans receivers are of only 2 because the maximum data is 16 bit only. So 8 plus 8, it is 16 bit. So with the help of the DT slash R bar and DEN. So both are nothing but data transmit or receive, which tells you about the direction of data, whether we're going to store the data or we're going to read the data. So through this pin, we can able to see that. And data enable is also active low signal. Whenever this pin is active, whenever the pin is low, the bus is carrying the data. So this is the minimum mode configuration. If you're going to select input or output device means through the chip select also we can able to select the CS IO, that is the input or output device. Here we can able to read or we can able to write. Write means we're going to store the content into the IO device. The reading means we are going to transfer the data from the input output device to the microprocessor. You can see the configuration here. So I told you, no, everything is tells you about here. The minimum pin is connected to the logic one, so it is in minimum mode. It consists of a microprocessor, latches, transceivers, clock generator, memory, and IO devices. The interrupt acknowledgement is also an active low signal. Whenever if you connect an IO device or something, it gives you the signal which nothing but the acknowledgement, that is the recognition of the interrupt request. ALE, which tells you about whether the bus is carrying address. Whenever the bus is carrying address, this pin will be active. And data is a complement active low signal. So whenever the data is having that carry, it will be in 0. Okay, data transmit or receive. If the pin is 1 means data is transmitting from processor to any memory device or maybe IO device. Receive means it transfer data from memory or IO device to the microprocessor. So memory slash IO complement. If the pin is 1, the transfer or the data is through the memory. If it is active low means it from the IO devices. So write operation is going to store the content. Whenever the pin is low, we are going to store the data into the any type of device you are going to connect. Hold, if you are using a DMA operation, direct memory access operation, you can able to hold. If you ask for the bus request, you can able to get the hold. If you are granted for the bus to release, you can able to give the acknowledgement. And then latches, we are using the 74LS373 latch, which differentiate the address and data bus separately with the help of a ALE signal. And the address latches are only available during the T1 state, the first state of every instruction. So this are all I told you. The 8284 is a clock generator. It provides the entire clock signal period to the 8086 microprocessor. It also provides reset signal, wait state logic, and even lock signal also. Then we go for next configuration, maximum mode configuration. Here in this maximum mode configuration, the 32nd pin same, the minimum or maximum mode version is connected to ground, because here if you're going to act as a maximum mode, it should be active low. So if it is connected to ground means the logic is 0. So if the pin is connected to 0, the processor is going to act as a multiprocessor configuration. But here also we need the clock generator to generate the clock pulse for the entire microprocessor and entire operation here. If your microprocessor is going to act as a maximum mode configuration, then many number of processors or many number of peripherals is connected with your 8086. So the bus is common. Here to solve this problem, the bus problem, we are connected to another one that is called 8288 bus controller. So the bus controller, what they will do, they will have a logic to provide the bus to the any devices or something with the help of some token system or maybe with the help of the priority system. Okay. Other than that, you can see here everything is same. Chip select logic is same. Latches and transceivers, data buffers are both are same. So either you're going to connect with the RAM, that is a cache memory, or maybe a permanent storage memory slash IO memory. So the only difference is here the bus controller. Whenever some peripheral is going to ask for a bus, okay. So depend on the priority of S0, S1, and S2. All the three are status signals, which gives you the exact status of your edge microprocessor, whether to provide the acknowledgement or not. If they provide acknowledgement, the bus can be released. Sorry, the bus can be released, and either they can able to provide the uh, bus to the memory or maybe IO devices, whether it depends upon the operation of read or write, which also gives you the data transmit and receive operation. ALE at every T1 state, the address will be latched, and the next state itself, the data will be enabled. So with the help of bus high enable, whether the bus is having the upper byte from the lower address or the upper byte from the higher address, we can able to select this. Same, the S0, S1, S2 indicate the current machine cycle, where the Q status 1 and Q status 0 indicate the status of the instruction queue. So I told you in the class itself, these three status pins will have the 8 different what we can say that process. So if all the pins are active low, then it should be inter-acknowledgement provided. If 001 means it is input or output device read operation, and 010 is the input output write operation. If 011 means the processor in halt condition. If 100 means the processor is accepting the instruction and fetching it or decoding it. If 101 means we're going to read the data or from the memory, it may be address or read data. And write means we're going to store the data into the memory. And if all the pins are 1 means all are in reset condition. Okay, it should be a passive. The data will be inactive, right? Because it's not S1, S2 or complement active row signal. If all the pins are given one means what happens? It should be a passive condition, right? And log complement bus is reserved by one processor. If anyone is getting the bus from the master, then they have to provide the log bus. So the other processors will still status of the log pin. If it is log means they will not ask for any request. Okay. So the bus request and grant we are having two pins. So at the time they can able to provide the access to two processors, and we have separate logic also here to provide the bus release to the streams. And coming under this multiprocessor system, uh, we have three basic configurations. One is coprocessor, another one is closely coupled, another last one is loosely coupled. So in coprocessor means like a assist to everyone. So whatever the work is performing by the master, okay, the slave can able to do something. At least they can able to help for the master. So that is one 8087. If the 8086 cannot able to do some process like a floating point operation, integer point of operation, the coprocessor can able to help for this type of operations. We will see one by one. Okay. And if you go for coprocessor, sorry, closely coupled configuration means nearby like a friend, they can able to share your work and all that, like a master or a host. So first you go for the coprocessor configuration. With the help of a diagram, you can able to easily know it. I will show the diagram. So here the master, the 8086 or maybe the 8088, both are 16-bit microprocessor. So here, whenever the escape instruction is being executed in the master, it automatically wake up the coprocessor. Okay, till that the coprocessor wait for the instruction for the command from the master whether to do the work or not. Whenever this instruction is executed, the 80 coprocessor will get the data from the 8086. Before that, they will deactivate the test pin and execute whatever the operation is having that. They will perform one by one. In the remaining time, the 8086 is also performing their own operation execute instructions, and for the result, they will wait till the coprocessor finish that operation. After the coprocessor is finished the operation, then they will ask for the bus to transfer the data. So it immediately activate the test bar pin. So the test bar is active low signal. It will give the low signal test pin. Then the 8086 can able to know that okay, coprocessor has been finished the data operation. So they will go going to provide the result. So the 8086 will tell wait for the result to provide. Okay, this is the coprocessor configuration, and next one is closely coupled configuration. So here all the devices are connected with a common bus. So the coprocessor cannot able to take the control bus. Only they can able to access from the master. Closely everything to the CPU. That's nothing but. So the 8089 is also another closely coupled configuration, or you can also call as tightly coupled configuration. They will share both the clock and bus control logic. In coprocessor, they will share only the bus control logic. So instead of using escape or wait instruction here, it's an independent processor. The 8089 is like I told you, that's like a friend. They can execute its own operation, and whenever the master asks for the data, they will be able to provide. So it is a host set up a message in your memory. I have given you work. Okay, you can go to this address and you can able to do the operation one by one. Likewise, they will give the operation. The host will be able to get it and they will do the control their own operation. So whenever the completed operation, it will give you interrupt to the master, sorry, interrupt to the host processor, and I told that the data is ready. So you can see that the 8086 initially set up a message. So this is the work of your, that's nothing but independent processor. Then 8086 will go for the instruction like out. So what happened? The independent processor have been indicated that this out instruction is available. So we have to go to the specific address. What are all the work they are provided in the message? So then they will take it and execute one by one. Okay, till the process has been complete. And 8086 will monitor and will execute their own instruction. So in the program sequence. And whenever the data is ready, the independent processor will notify the completion of the work. And if you need means you can take the data like to the 8086 processor. Then they will wait for the ready or interrupt request. Then they will transfer the data from the host to the main processor. And the last one is loosely coupled configuration. Here, not only a single core processor is not only a single independent processor. Here, many number of processors are connected together. Okay, so the work has been equally shared. But here, the only one problem is that the bus arbitration problem, because you can see the diagram. This is module 1, this is module 2, this is module 3. So every module will have that like that nothing but each loosely coupled coprocessor have a closely coupled configuration and a coprocessor configuration. That's nothing but. So it is one module. Likewise, all other modules. So the system memory is common and IO device is common. The bus is also common. So if one module take the bus and they granted for it and they are going to transfer means the other two module has to be waited and it doesn't know when the module one will be completed. So this is called the bus arbitration problem. This can be solved with the help of three methods. Not I can be solved, but I can able to reduce this uh, what we can get delay problem one by one. The first one you can see daisy chaining method. Here, what they happen, all the modules can be connected with the controller based upon the location of the processor they nearby. They can able to get the bus easily. So you can see that the master one is nearby the controller. So whenever they ask for a request, because a request and a bus busy is a common for all the masters, only the bus grant signal is given to the first device, from the first device to the second device, and second to the third, likewise. So if the first master is in need of a bus request, they immediately call the controller and ask for a request. So if the bus grant has been given, the bus busy will be activated. No other masters can able to ask for the request. But if like this, there are 50 number of masters connected. If a 50th module is going to ask for a bus request means, even they will go for the ask request is a common line. Immediately the control what they will do, they will provide the bus grant release not to the exact 50th module, they will give it to the first module only. So after the first module doesn't need, they will transfer the module to the second token, like a token to the second. But in between the 15th module, if any other module is immediately request or ended of the bus, okay, if they got a token, they are using means what happened, the 15th module request has been cancelled. Sorry, the grant will not be able to go. So the 15th module will be wait till the token has been receiving. So they will wait for the till 49th module is going to pass the request. That is the method problem here to solve the bus arbitration. This is called a daisy chaining. And second method is a polling method. So I cannot able to provide the token to one by one. So all the lines are given provide separately to the individual modules. So if anyone is in need of bus, they will ask individually through a logic module. So if the three lines are there means the three lines up to 8 devices can be connected, up to 8 modules can be connected. If like example, the three possibility means 2 power 3 is equal to 8. If 000 means the first module is going to ask a request. If it is 111 means the last module is going to ask a request. So through this request, we can able to observe. If you have 50 number of modules, same like daisy chaining, what happens here means for the probability, we need more than 3 number of lines. Okay. So what happened? It somewhat look like a complex if we go higher and higher rating. And also the signal lines will be very costly when compared to that here. So that is the problem in the second, that is the polling method. And the last method we can able to eliminate these two methods disadvantages. That's nothing but a independent request. So we are providing each request and grant signal separately to every modules. So if anyone is asking the request, the other module cannot able to know that which module has been asked the request or which has been providing the bus or something. So here the bus busy signal only is common. All other lines are separately given here. So we can able to avoid the disadvantages of these two method request problems. So this has been given your generation. You can able to know in the PPT. So students, that's all about today's topic. If you have any doubts, means you can contact me at any time, and you can able to solve it as soon as possible. Thank you. Have a nice day.